Hello everybody, welcome back to my channel, and in this video we will be covering the limit definition of the derivative and showing how pretty much all of the basic rules can be derived from that same definition. So without further ado, let's dive right into it. Over here is our definition. F dash of x, or the derivative of f of x, is equal to limit as a variable h approaches 0 of f of x plus h minus f of x divided by h. Now, what this is basically the derivative represents the slope of the tangent line to a function at that same point. Now, if you didn't know that, you could also watch my Intro to Calculus series, which covers a lot of the limit rules and will provide the foundation for this video, as many of the rules covered here are very similar to the limit rules which I covered in my Intro to Calculus series. And then why we need limits is to avoid a division by 0 when we're calculating the rate of change to show what it approaches overall. Let's see if this definition works. So let's find the derivative of f of x is equal to x squared using the limit definition. So first things first, we have to actually state our definition, which is f dash x is equal to limit as h approaches 0 of f x plus h minus f of x divided by h. Then f of x is equal to x squared, so x squared will place the f of x, and then the x plus f of x plus h will be x plus h squared. Now, if you expand it, you'll get x squared plus 2xh plus h squared minus x squared over h. Now, what you might notice is that we already have x squared and negative x squared, so that's our next step to simplify the numerator. So we have f dash of x is equal to limit h approaches 0 of 2xh plus h squared over h. That's a lot of h's, and then we have to factor out h to get limit as h approaches 0 of 2x plus h. Now, let's take the limit. So if h is approaching to 0, that means limit h approaches to 0 is 2x plus h, now 0, so 2x plus 0, which is equal to 2x. And that's the result right over there. Now, if you didn't realize already, this actually is the same result you would have gotten if you had just used the power rule. So it's a proof that this actually works. The main proof for this video will be to prove the power rule. So to prove that d over dx of x to the power of n is equal to n times x to the power of n minus 1, and we have to start with the limit definition. Over here is the entire approach, if you can read it. Otherwise, in the next few slides, or the next two really, I'll explain how all of this exactly ties together, and it'll be slightly easier to understand. But if you think you can get it just from this, feel free to pause the video and make sense of it on your own. The first part of the proof is to expand x plus h to the power of n using the binomial theorem. So the binomial theorem says x plus a, or anything, we're going to say h here, is equal to x to the power of n plus n times x to the power of n minus 1 times h plus n times n minus 1 over 2 factorial times x to the n minus 2 h squared plus so on, and then you get plus h to the power of n. And yes, this in fact works for every single power. You can test it out if you want for a couple powers just to make sure that it works. And now we'll substitute that into the limit formula. So what we get is limit as h approaches 0 of x to the n plus n times x to the n minus 1 times h plus n times n minus 1 over 2 factorial x to the n minus 2 h squared, so on, plus h to the n, and then at the very end we have minus x to the power of n. And the reason that's important is because in the next step, we're going to simplify. So it's going to be x to the n and x to the n will just become 0. So there is a simplification in this step. Then what we can do is we can factor out h because every term after that contains h. So we have n times x to the n minus 1, so on, so on, so on, then plus h to the n minus 1. Then as h approaches 0, all the terms containing h vanishes. So what we're left is n times x to the n minus 1, and that is the power rule. So the derivative of x to the power of n is equal to n times x to the power of n minus 1. Let's move on to the constant rule. This is actually one of the most simplest things. Rule is d over dx times a constant c is equal to 0. So all the proof is since c is equal to f of x and doesn't change no matter what x is, it's going to be c, then minus c over h, then 0 over h is just 0. And the geometric interpretation of this is that the horizontal line has no slope. That means it can't have a derivative, or the derivative is 0. The proof for the constant multiple is a bit different, but also likewise much simpler than what we saw above with the power rule proof. So d over dx times c times f of x needs to be equal to c times f dash of x. So if we use the proof setup, limit as h approaches 0, cf times x plus h minus c of f of x over h. Then we factor out the constant out of the limit, and it just becomes c times f dash of x. Now, if you don't understand how this works, you can also watch my Intro to Calculus series where we cover a lot of the limit rules, like the constant rule in limits, where you can factor out the constant from a limit. So that's why I mainly recommend watching my Intro to Calculus series first, as what I covered there is the main foundation and and a lot of things there you'll need to know before you start calculus. Here is the sum rule, where if we have the derivative of two functions added together, that's equal to the sum of the derivatives of both the functions. So we have f of x plus h plus plus g of x plus h, so on and so on. Then you can rearrange the terms for limit properties. After that, what you'll need to do is you'll need to factor it out, but that's going to be covered in this slide. So we separate this into two limits, which is another limit identity. You can split this up and separate it into multiple limits. Then the result is f dash of x plus g dash of x. And this works for any finite number of functions as long as they're all being added up together. And for subtraction, though, we have the difference rule, with the proof pretty much the same thing as the sum rule using linearity of limits, and the only difference really is that it's negative. But what we can do is actually we can do f of x plus negative g of x, so that essentially becomes what we can substitute for the sum rule proof, and there you go, ta-da, you have it all there over there. And the same thing for the sum rule, since it's pretty much just a special case of the sum rule, we can use it for any finite amount of functions. The main beauty of this foundation is that it's one relatively simple definition, but it generates pretty much all basic derivative rules and even some more complex rules, like the product rule, the quotient rule, and the chain rule. I'm showing you the product rule, the quotient rule, and the chain rule. And then, of course, the final thing is that they all ultimately trace back to the limit definition. And I'll cover how they do it when I cover each of these individual rules. Here are a few applications before we go. The first is in physics, velocity and acceleration, and economics, which is marginal analysis, and engineering, which is optimization problems, which also can be pretty much in calculus itself. Now, the reason all of these are there is actually because these use derivatives and integrals, which all ultimately stem from the fundamental rules of limits. Thank you so much for watching. See you in the next one. But before you go, please make sure to watch my other series. They're really good. I promise you won't regret it. And please make sure to like and subscribe and hit that notification button for more awesome videos just like this. And please make sure to comment down below just in case if you have any suggestions, any topics I need to do, or anything I should clean up. I'd be happy to help because I want to make this channel a place where anyone can come and learn topics without being intimidated and someone conversing to them instead of trying to be a teacher, just really trying to help them and really make them understand. And I respond to pretty much every comment as long as it's not asking about my age, location, or any other personal information. So thank you so much for watching. See you in the next one, and bye-bye.